Okay, so our topic today is analysis of uniformly tapering circular rod or bar. Okay, we have a circular bar which is having uniformly varying cross section. Is there someone trying to say anything? Yeah, I can just hear that sir word, but the rest of the word I cannot hear out. Please type it in chat. The diameter here is D1, diameter here is D2, and the length of this bar is L. Now this bar is under a tensile load of P force. Okay, zooming in is a very difficult task. Let me see whether I have that option or not. Is it necessary to zoom? I cannot hear you.
ফেটে যাচ্ছে স্যার।
ফেটে যাচ্ছে। Whoever is talking, I cannot hear you. Please type. Okay, I'm trying. Let's see. This is the scenario here. We have a uniformly tapering cross-section bar. The cross-section is circular. Now at the one end, the bigger end, the diameter is D1. The smaller end diameter is D2, and the length of the bar is capital L. Now in this case, the bar is under tensile load of P. So we have to find out what will be the elongation in this case, or in this type of problem, what will be the approach where the cross section is uniformly varying. In that case, what will be our approach? Okay, so this is uniformly circular. If this bar was uniformly varying but rectangular cross section, then also same procedure you have to follow. Procedure will be same, answer will be different for different cross section. Now let us find out what we have to do. From any one end at a distance of x, we will take a cross section of thickness dx. Okay, this thickness will be dx. This is taken at a distance of x from the first end or from the bigger end. Okay, so at a distance x, we have taken a cross section dx. Now this is a strip of thickness dx. Now the dx is so small that we will take that the cross section is not varied there. So in such a case, the diameter at x dx will be written as d1 minus d2 by capital L into x. Sarveshwar Rajguru, whatever you are saying, I cannot understand. Please type. Sunny Singh, same thing also. Please type. Now, so this d1 minus d2 by L, this term is a constant, because d1, d2 and L are defined. So we can write d1 minus kx, where k is a constant. So we can write k is d1 minus d2 by L. Now we have known that diameter at position x. Now ax is equal to pi by 4 dx square. Cross-sectional area at x section is pi by 4 dx square. So which is literally pi by 4, putting the values, d1 minus kx whole square. Now the stress will be there is load by area, that will be P by pi by 4 d1 minus kx square. Now so we have found out the stress at that particular position. So the strain can be found out by the formula stress by elastic modulus. As we know, stress is directly proportional to strain up to elastic limit. So when it is under elastic limit, we can say that the strain will be stress by elastic modulus E. Now putting the values again, we can get, we have the value of stress here. So P, this 4 goes up, it becomes 4P by pi E d1 minus kx whole square. Okay, we are just putting the value of stress we have just found out. So strain is found out. Now again, what is the strain? This strain is the elongation of dx. Previously it was dx, the thickness was dx. Upon loading of P, the dx has been changed. That's why this strain has been created. So now, so the extension of dx is delta x, can be written as strain into original length dx. So it can be written as the value of strain we have just found out, 4p divided by pi e d1 minus kx whole square into dx. Okay, so this is the elongation of the thickness dx only. Now if we want to find out the total elongation of the bar, then we have to integrate this equation up to a limit from starting here at 0 to L. We have found out the extension of dx. If you want to find out the extension of the whole bar, of the whole length, then we have to integrate this elongation of dx or del x, and the limit will be from 0 to L. So we will find that out. Total extension. Total extension means dl, and that can be written as 0 to capital L 4p dx by pi e d1 minus kx whole square. Okay, so now you have to do the integration. So after integrating it, you will get 4p by pi e k into 1 by d1 minus kl minus 1 by d1. Okay, I am not doing the integration in the class because we have very less amount of time, and you can do the integration by yourself. Now when we get this value, there is k. Now we can put the value of k back in here. After putting the value of k, after calculating, you will find, so let me write it here, after putting value of k, you will find finally dl will be equal to 4pl by pi e d1 d2. Now if the rod is of uniform diameter, then d1 will be equal to d2, and as a result we will get the total elongation of the bar 4pl by pi e d square. So is the expression clear to you? Give me a response.
Sir.
I could not hear you properly. Turn on your mic, wait for 1-2 seconds, then start talking.
Ye-
Which part? Which last part? We are just putting the value of k. The value of k is here, d1 minus d2 by L, constant. We are just putting the value of k. What we get from integration, we are putting the value of k, and furthermore simplification, we will finally get this value. So here the bar was circular. If the bar was this way, reducing cross section, but of rectangular cross section, so in such case your only difference will be in this area. The only difference will be in this area, and the procedure will be same. Now the question is, how did you find the value of dx? You just look at the figure, it's simple geometry. if the variation of length is capital L, for this capital length, so for this length capital L, for this length of capital L, the variation is diameter is d1 minus d2. So for this x length, the variation will be how much? This much. Now if the variation is this much, you just subtract this portion from this bigger diameter, you will come to here. Look at the figure just. For this L length, variation is d1 minus d2. So for unit length, variation will be d1 minus d2 by L. For x length, it will be d1 minus d2 by L into x. Is it clear now? Fine. So this is the task to all of you to find out the elongation of a uniformly reducing cross section of rectangular bar. Okay, you get that? Find out the elongation of a uniformly reducing rectangular bar of length L. Just similar problem that will be having a rectangular cross section. Okay, in any book you will find that, but you try to do it yourself. We will go to next topic. Our next topic is analysis of bars of composite sections. Let me write it out. Analysis of bars of composite cross sections. Okay, analysis of bars of composite cross sections. Now, first, what do we mean by this composite cross section? Okay, we are giving out an example here. Let us have two bars under same condition, or you can say a single bar has been made of two different materials. Okay, this is a bar, this is made of one material, this is made of another material. Okay, both are rigidly fixed at the bottom as well as on the top. Both having length L under load of P. For a similar case, you can assume that there is a tube covering up another material inside it. Copper tube over a steel bar. Okay, both sides are rigidly fixed. It is under some load, or you remember just the concrete reinforced by steel bars. Okay, so this is concrete, these are steel bars. So these are the example of composite bars where a single bar having two different material. The definition says a bar made up of two or more bars of equal lengths but of different materials rigidly fixed with each other and behaving as one unit for extension or compression when subjected to an axial, tensile or compressive loads is called a compressive bar. So is the compressive bar concept clear? Problem still continuing. Now, is this scenario clear? Okay, so now we will go for the analysis. We will find the equations what we can uh, write for this case. So as we have discussed, the load, total load will be shared by two different bars, and the load shared by bar 1 is P1, load shared by bar 2 is P2. The stress in the bar 1 will be then P1 by A1, and the stress induced by bar 2 will be P2 by A2. Now, then from here we can write that P1 is equal to sigma 1 A1, P2 equal to sigma 2 A2. So we put it in this equation and we get P equal to sigma 1 A1 plus sigma 2 A2. Now, so we have the stresses, so we can get strains also. So the strain in bar 1 is sigma 1 by E1, strain in bar 2 sigma 2 by E2. Now we have strains. Now, as you can see, look at this bar. Hold on a second. Yeah. Now, this strain at bar 1 and strain at bar 2, if you look at this figure, you find that these both ends are rigidly fixed on this bar 1 and bar 2. So if P is applied, the strain in bar 1 and strain in bar 2 will be same. The elongation here and here will be same because these ends are rigidly fixed. So if the elongation are same, the strains are also same. So here we can write that strain at bar 1 will be equal to strain at bar 2. So we can write sigma 1 by E1 will be equal to sigma 2 by E2. So this is one equation, this is another equation. With help of these two equations, we will be able to solve this type of problems on composite bar. Okay, we will quickly solve a problem we will quickly solve a problem. Okay, inside that is steel rod and this is a copper tube. Sorry, this is a copper tube. Okay, this length is 15 centimeter. Draw the diagram please in your copy. Steel rod having diameter 3 centimeter. This is 4 centimeter and this is 5 centimeter. And the whole system under a load of 45 kilonewton. Okay, so the steel rod of 3 centimeter diameter hold on a second, I have a phone to attend. Sorry for the inconvenience. I use my phone as webcam. That's why all the problem comes in when a call comes up. Give me a moment. Give me a moment. I'll reconfigure. Yeah, just came back. Okay. Okay. So there is a steel rod inside, you can see in the image, of diameter 3 centimeter, enclosed centrally in a hollow copper tube as in figure, of external diameter 5 centimeter and internal diameter 4 centimeter. Now the composite bar is then subjected to an axial pull of 45 kilonewton. If the length of each bar is equal to 15 centimeter, which is shown in figure, then you have to determine the stresses in the rod and the tube. So you have to find out sigma 1, sigma 2, where 1 say for steel and 2 say for copper, or you just simply write sigma S and sigma Cu. It will be much clearer. Sigma S, sigma Cu means stresses in steel rod and copper is to be found out, and as well as you have to find out load carried by each bar. That means PCU and P steel. Is the problem definition clear? Give me a response, Avronil.
Yes, sir.
Okay.
Yes, sir.
Okay, fine. So there is a steel rod inside, there is a copper tube outside. Both are attached very rigidly and having an axial pull of 45 kilonewton. The dimensions are all given. So from here we can find out. Now you see the lengths are in, one is in kilonewton, others in centimeter. Okay, so our job is to convert all of these in a single unit, where E is also given is 2.1 into 10 to the power 5 Newton per mm square, and this is for steel. This is for copper. Elastic modulus for copper is 1.1 into 10 to the power 5 Newton per millimeter square. Okay, so now our job is to write. Okay, our time is up. It's 10:50 already. We will continue the next class from here.